All right, so today we are working again on proving, well, basically this. So we have some function here that takes a natural number and returns a set, and the construction here is that each one of these, for all n, the function set seek of n is 1, infinite. 2, the union of all set seek covers all natural numbers. And then the third thing being that for any two set seeks where the inputs are different, they are pairwise disjoint, meaning that their intersection is empty. So what I'm actually going to do, and I haven't done this in a while, but we are going to take all of this work, okay, and we are going to, oops. Okay, so now we have a totally empty document. Let's just start with import mathlib. I think it's just import mathlib. I think that's it. I don't know if that's hella slow. Okay, so we're gonna start off. So remember, let's pull up. Okay. So let's just go to the problem. So the statement of the problem is produce an infinite collection of sets A1, A2, A3 with the property that every AI has an infinite number of elements. AI intersect AJ is equal to the empty set for all I not equal to J, and the union from 1 to infinity of AI is equal to the natural numbers. So I'm just going to copy this and see how it plays out. Okay, so first off, we are going to come up with a definition. Definition is perfect power. It's going to be M of type N. And it's going to, and basically, M is a perfect power if there exists an NK. I don't know, such that, let's see, I forget exactly the syntax, so we're gonna have to refer, but such that n to the k equals m. We're gonna say also k is greater than 1 and n to the k is equal to m. Oh wait, I think what we're supposed to do is I think you're just supposed to do this. And let's just check that that's actually right. Oh yeah, so what we did the other day is we proved lemma 0 is perfect power, and the statement of this lemma is basically is perfect power 0 by, so first we're going to unfold is perfect power. Okay, then we're going to say use 0, and then I think we have to do use 1 or 2, and then simp. Okay, so there we go. So this was the proof that 0 is a perfect power. We can also do, and it's the same proof really, 1 is perfect power. It is basically the same proof. Use use wait, actually, is this right? Okay, so let's see, is my game good? All right. So okay. All right. So this is wrong though. 0 to the 2. Wait. Wait, what? This is like, look, if I do eval 0 to the 2. Wait. Wait. But eval 0 to the 0 is 1. Wait, what? Wait, am I tripping? Zero to the 1 makes sense that it's 0, but 0 to the 0 being 1 is so weird. Okay, well, in any case, 0 squared is 0. So in this case, we just use 1, use 2, simp. Okay, so we've now proved those basic things. Now we want to prove I think it was called utility, but we want to prove that for some m of type n, and I think you put it here, right, where m is greater than 1. That's and but what you have to do is h or something like that. We want to prove that exists unique n of type n cross. How do you cross? How do you do it? Oh, slash x. As the tuples such that n dot 1 to the n dot 2 is equal to m, and n dot 2 is greater than 1. Wait. We're trying to say that for any natural number, there is let me go back. Okay, so the first one is not a perfect power, and okay. So there was no constraint on. Oh, which makes sense. Yeah, obviously that's true. Okay, so I'm just being silly. So yeah, so this is nonsense, but not. Oh my gosh, not is perfect power n dot 1. Do we get the syntax? So I need that comma. I always forget the comma. How will you do it? Is exists unique n of type n cross n, comma. I think that's right. Did I use the wrong cross? I think it's just a glitch. Oh, you know what? It might be. Wait, what is this? Oh. So what is the other one? I don't know what the other one is then. Hey, anyways, we're good now. All right. So we are still working on proving this. This is sort of the this is sort of where we're at. And so so what we want to do is we want to say that we want to make a lemma where if we have some random natural number n, it's either perfect or it's not, and I'll show that. So basically, for n of type n, is perfect power n or not is perfect. Is perfect. It's so annoying how bad the Okay, and then this is, we can just say apply classical.em, and that's the whole proof. I'm pretty sure. Why is it so slow today? Okay, so basically this is a standard, this is just like fundamental math. If you have some proposition and the negation of that proposition, well, one has to be true, otherwise everything falls apart. So this is called the law of excluded middle. So so we can say have HM of type this, and we just change these to be M, and we say by N perf or not of M. So now we have introduced a new hypothesis into the tactic state, or the state of the proof. And so then what we want to do, we want to say cases HM, and then I think some little light bulb, some little light bulb is supposed to show up. Generate an explicit pattern match. Okay, great. So now we have two little arms. In this arm, we need to now deduce from here that that there exists a unique N where N1 is not a perfect power and N1 to the N2 is equal to M. So this case is the case that I'm still working on. So we're going to leave that sorry in there for now. But then this case is actually easy, and I'll show why. So let's see. How did we do this? I think we just start with use M1. Okay. And now we do, so what I'm saying here, what this is doing, let's go back before this, is we're saying there's a unique N. So what we're saying is, okay, that unique N is going to be M comma 1. And what that's going to do is that's going to now turn that into the conditions for proving that it exists, meaning it satisfies the condition, and that construction is unique. So what we're going to do here is we're going to now do apply and dot intro. And I don't exactly know all of this. Wait, let's just do this. Does it go? I think you're supposed to do this, right? Okay, there we go. So now what apply dot and intro is it took that and it split it into two things. Now I'm pretty sure I can just use simp for the first one. Oh wait, so we want to do a dot. So the dot means take the first goal, because there's multiple goals, so we're taking the first one. At least that's how I interpret it. So we're just going to do simp, and now exact H. Then we're done. No goals. Man, I missed the little ta-da. Dude, I missed the ta-da. Okay, so now we want to take the second one. We want to show that it's unique. So what this goal state is now saying is that for all y of type n by n, if you apply y to basically the goal, then that implies that y has to be M1. So this is a way to say that it's unique, that there's no other one, because the implication is for any arbitrary y, if it satisfies the conditions, then it must be equal to the what we used above, which is M comma 1. And this is part of it that I don't exactly remember how we proved it. But let's just start with a simp. Oh, no. Wait. Um, well, let's think about what is this actually saying. Okay. So the reason why this is true is um, because we need to use the definition of perfect power. So the fact that H says that M is not a perfect power means there does not exist values for N and K. So what we're going to do is we are going to rewrite is perfect power at H. And so now we're saying H says there does not exist an N, does not exist a K greater than 1, such that N to the K is equal to M. Um, so how did we do this? How did we do this? Okay, I don't want to cheat quite yet. I want to think about it. How do we use the fact that there does not exist? I'm pretty sure that the way that I would really do this is by contra. Let's see what by contra. Okay, so we assumed that the implication is false. Okay, that's probably too loud. How about this? All right. So, okay, so I don't have the most time because I do need to study for this test. But why? All right, I'm gonna cheat. Let's see. What exactly is the start of utility? Exact B. Oh yes, that's the simple part, right? But then here, intros. So what does this do? Oh wait, we don't get. Okay, on diffs, I guess lean doesn't. Okay, so we introed. So what did that do? So that took this for all, and then it turned y into some arbitrary n by n, which, okay, that makes sense. And then it introduced the hypothesis that, okay, great. And now, okay, right. Okay, so intros is what we wanted. Okay. Let's see, what did this do? Okay, so, obtain just splits it. Okay, cool. So this is where things not perfect power. Okay, great. So let's try to apply. Not perfect power implies. Right. Okay. So let's just see if we can take this. And start to work on it. Why does it keep... Oh, because the diff changes. I get it. Okay, so somehow we're able to say... Oops. Apply H. Okay, that part doesn't make much sense to me. So X falso does what exactly? What? X falso adds... Okay, so the goal up here is we need to prove that K is either 0 or 1 when M is not a perfect power. So then X falso... So okay, so what we're saying is that assume this is basically a contradiction in proof. So we assume that K is greater than 1. Okay, so now we add that to our hypothesis, and this is the first case. So if we go down here and do this, then we say K is not greater than 1, and we want to prove that this is. So now we go up here and we say, all right, we're trying to show that this is impossible, so we rewrite the goal to be false. But now I don't really understand how apply H. Hold on, let me get my hat. Why is it that apply H takes false and negates it? In this case, the goal is to show a contradiction because M cannot be a perfect power given given H. Because you're now trying to derive... Okay. This uses the hypothesis of H. What does apply H do? It means that you're trying to satisfy the conclusion of... What? It means you are trying to satisfy... Yeah, what is the docstring of apply in general? Apply tries to match the current goal against the conclusion of E's type. Oh, okay, yeah, that sort of makes sense. What's the next step, though? What? I don't understand that at all. So wait, let's just try to do it my way. So rewrite. Oh, okay. Here's maybe a way to put it. So we had as a hypothesis that M is not a perfect power, and we're doing something by contradiction. So the goal state is just to prove false. And so we can say apply H to now rewrite the goal to say if we can prove that our current assumptions allow us to derive a contradiction, meaning both is perfect power and not is perfect power, then we're done to show that k greater than 1 is not possible. And we're good. Okay, so now the second part of this is this should just be simp, right? Okay, so fine. So let's do the cases. What does cases k do? What does cases k do? Dot right semi. So this is, I definitely didn't write this because I've never used a semicolon really. Oh wait, what is this dot? Is this the normal dot? Center dot. I think normal dot works too. But so let's say left and do this. Right. And that does it. What was the proof state here, just so I know? So we're saying that it's not true that n plus 1 is greater than 1. So then, yeah, okay. Sure. I sort of get this, but not exactly. But now we want to prove, so now we're at here. And I think what we're trying to prove is we now need to show we basically just need to copy this into there. So the thing is going to be n equals m and yeah, right. This is another like contradictory thing where it's like if y1 wasn't a if y1 was a perfect power, let me just get a notebook. So not m is not a perfect power, and we're saying n.1 is. Then that means that this implies there exists n a k a k a greater than 1 n a to the k a equal to n. Oh wait, this is y. But in any case, and we're saying we also know that n1 and 2 but then you could rewrite n1 as na ka n2 equals m. And um, okay, so I think I've worked it out. Um, Wait, where are we? Oh no, we're down here. Use M1, apply simp exact B. Oh, yeah, so we did that. And we split this. M is greater than 1 by assumption? Yeah. I don't think we did this. We didn't do this yet. So not perfect power, unique solution. So yeah, M is not a perfect power. M is greater than 1. We have some A and B. So A, okay, great. Jeez, but I don't know what I'm doing. Okay, yeah. So we wrote this thing that allows us to say that if M is not a perfect power, and we have an AK pair that equals M, then the only possible solutions are that K equals 0 or 1. So we should be able to say, do we do a halve there? At H. What is H in this case? What? I don't get this. I'm like, I was like in the zone a couple days ago, and now I'm like not. Oh wait. Okay, wait. Yeah. So okay, this is this modus ponens thing. So we have this implication that we know now that okay, before H was that it's not a perfect power, and now we can say that. So wait, we should be able to actually apply H here, right? There we go. So we actually did the. I don't know. I don't know. Have foo type uh, b equals 0 or b equals 1 by applying HAB to H. Okay, that checks out to me. That makes sense. Because, so now we need to do the cases. Okay, so the case of by cases foo. Wait, right? Oh, yeah. All right. Let's just do cases prime. Okay, so we're trying to show that with the assumption. All right. Let me just try without looking. No, yeah, we need to just at the outset. You need to just be like, ex falso. Okay, wait, yeah. So that's like rewrite foo1 at HAB. And then how do you, okay, so now the question is, now that we have two contradictory things, how do we use them? Okay, apparently Linarith is able to figure that out. Okay. Okay, that didn't work. Oh yeah, we should just be able to do exact HA. How do you do it? With Langles? Alright, let's just do exact HAB. Okay, I guess you have to Langle it. Ah. Great. So now we can just we can say exact and we're going to apply H. What else do we need to apply? HM. Where did this M greater than 1 come from? I thought that was H. Um, case A, case B. Okay, so now it doesn't rewrite it as a freaking dumbass thing. We should be able to say exact this thing by case B H. HYA. How did we do it? Oh, you apply M y.1 y.2 at HYB. Okay, wait. What was HYB? What? This is the exact same. Oh wait. Oh wait, we just did the wrong one. No? I don't know. Okay, so there's a number of things going on here that, yeah, I feel like I'm not feeling it today. Like, it's not clicking. Like, I'm just copying it over. So, I don't understand what's different. Let me just copy this whole thing. I'm so confused. Oh, wait. Why is cases there? Wait, okay, I should be able to say apply H at case B. What's the modus ponens thing, though? Can I do a list here? So we have both of these things. So we should be able to why is it cases? Wait. Obtain this from HY, and then rewrite HYB. This is supposed to be HYB. Bro, I'm tweaking out. What is going on? Alright, I'm just going to, does this run now? Wait, what? Dude, I don't even know what I'm doing right now. I'm like such a clown. Like, I genuinely don't understand. If I were to just copy this into this document. Okay, intros YHY. Obtain. This thing is so stupid. Why is it different here? Is it because this thing is switched around? I'm just going to copy this exactly. Because I don't even understand why this is... It's like the exact same thing. Oh yeah, no, it's... Okay, I'm so stupid. It's just the order was flipped around. Okay, I'm stupid as hell. The order was flipped around. Okay, so now... we have y1 equal to m and y2 equal to 1. And we're trying to then use that to prove that y equals m comma 1. This is just going to be like... This is like a... Even though it's like immediately obvious, it's like one of those things that's good to make sure you know. Because it's just how you manipulate data in lean. And I really don't want to look at the answer, but... Why is it cases? Okay, so what does the docstring of cases prime do? This doesn't error. So it is able to just rewrite HYB1. There's so much random stuff I don't understand right now. What does X do? Can I apply these in a list to make it shorter? Wait, what? I feel like there's error, these type mismatch. I think I should just be able to do apply. There we go. That was brutal. I couldn't even explain it. I feel like I'm more confused now than I was before. That was tough. So what... Okay, I get this branch now. This actually makes sense. So basically you're saying, so we assume that M is not a perfect power, and we have some A and K pair, and we then assume, alright, assume for contradiction that K is greater than 1, okay, and then you rewrite the goal state to say, okay, we want to show that if we assume this, then we can prove false, that something is wrong. So we apply H to the goal state, which means that we're now trying to prove the opposite. We're trying to prove now that we can show, if K is greater than 1, that we can show that M is a perfect power. So we rewrite the definition of perfect power, and then we use A as the value of N, and then we use the value of K, because we have a K greater than 1, and we have H power, so we can say this. And then I guess it's just automatically simplified the rest, which is a little bit... I would have hoped that after this, it would say that we still need to show... I think what it does is it says if after you use a tactic, the goal state is literally equivalent to one of the hypotheses that you have, then it automatically applies the hypothesis. I don't know if that's true, but it seems like what it's doing here. Okay, then now you're in the other case. You say, okay, so k is less than or equal to 1. And so you go to here. So k is equal to 0 or k is equal to 1. And we want to show that, right, so no, what it did is it inverted the by cases. And what I don't understand is why you put k there. Why do you put k there? Oh, wait, no, this is something else. So this is where it flips it around. Then we take the cases and we say either... Wait, what happens? This is actually a little fancy. Yeah, that's a little fancy, huh? But anyways, I mean, this proof I don't really care about because it's like, obviously, if k is a natural number and we have that k is not greater than 1, then it's got to be... So this is just obvious. So, so this proof sort of makes sense. Okay, so that checks out. Now we're saying we're going even further to say h is, if m is not a perfect power, m is greater than 1, and we have an AB, then A has got to be m and B has got to be 1. And we use HM. Let's see, if we were to delete HM, does this proof start to fail? Okay, so wait, let's just remember where we're at. So we, okay, so yes, we apply this thing with these numbers at h, where h is not perfect power. So then we get that k, or in this case b is either 0 or 1. And then we only get the implication because for some reason it doesn't find HAB. I don't know where you're supposed to put HAB, but in any case, that we just use modus ponens here. Do you really have to be explicit about this type? Shouldn't it be able to... Yeah, no, you don't have to be explicit about that type at all. So we're applying HAB to H. After we rewrote it so that now we have B is 0 or 1. Now we go into the cases where first we want to show cases of foo. So since we're trying to prove B is 1, we do for contradiction that if we assume B is 0, then we can't, that there must be a contradiction in here. But since we don't have HM, okay, so we rewrite POW 0, A is 0 equals M at HAB. And then linear, right. So if we add in HM, M is greater than 1, then we're good. Okay, now in the second branch of this, we show that A, okay, and then we just exact it with the Langles. Okay, great. So I don't even really want to commit this, but that's the walkthrough of this thing. Now I'm gonna go study. An hour and a half just to do this. I think what we'll do is we'll copy this. Is this the whole thing? Okay, so we're gonna say put this in here, take this, put this in here, and there should be no diffs. Cool. We can delete this. So what are the changes? Just utility. Okay. Started the proof over from scratch to solidify. All right, so that was pretty cool actually. Lean is kind of confusing though. I just got to get more comfortable with it, I think. All right.